Welcome to Texas State University's Chemistry 2330, Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin. We will continue with Chapter 5, Part 6, Additional Reactions of Alkenes and Alkynes, specifically the hydrogenation of alkenes. Okay, so the first reaction I want to talk about in the hydrogenation of alkenes is what we call hydroboration-oxidation. In this case, we actually take a compound called boron and we add it across that double bond. And then most of the time there's a second step, which we'll use in the alcohols chapter, to generate an alcohol on that double bond. Okay, so the idea of the result of this hydroboration is that we're going to add across of that alkene and then we're going to oxidize off the boron compound. Because the hydrogen in this particular reaction adds on the more substituted carbon, which is reverse of the hydrogenation we saw before in formation of alcohols, like the addition of water across a double bond, we actually can have the OH on the less substituted carbon. So the net result of this hydroboration oxidation reaction is that we get an anti-Markovnikov's hydration. Okay, let me show you a little bit more about that. So in the hydroboration oxidation step, the first step is actually the addition of the boron compound across the double bond. And the way it adds across the double bond is it takes a reaction of boron, which is boron is a trigonal planar with 3 hydrogens on it, right here. And so this bond here will add across a double bond, giving you a hydrogen on one side and the boron on the other, giving you a new sigma bond. And this can continue to react until all of these boron hydrogen bonds are consumed. And so we'll actually end up with a species in here that has 3 alkenes attached to the same boron atom. Okay, now we can most commonly use this is because boron is a gas, we typically dissolve it in a solvent like THF to give us this compound of BH3 in tetrahydrofuran. Tetrahydrofuran is a solvent we use frequently. It's an ether solvent, and we'll talk about those properties in a couple chapters, but this is a very non-reactive solvent, and we can use it as a support for this boron to give us this complex here, this complex between the boron and the THF to give a nice stable compound that still does this reaction across the double bond. Okay, so let's talk about the boron again. It's atomic number 5. It has 3 electrons in its valence shell, and it's one of the few atoms that doesn't follow the octet rule. So when it's in this octet, when it has these 3 electrons that it can share with 3 hydrogens in their outer shells, we can end up with a trigonal planar boron, okay? And it has an empty p orbital. Okay, but because it has all the correct number of electrons for the hydrogens and the boron, it actually has no charge. And so it is a tri-substituted boron with a neutral species. Okay, so that being said, that a lot of these boron compounds tend to be, quote, trivalent or have 3 bonds to other things, and it's a nice trigonal planar compound. Okay, again, boron's one of those things that kind of breaks the octet rule to form these kinds of compounds again and again. Okay, so I said before that hydroboration is both regioselective and it's also what we call syn stereoselective, meaning it's going to add them both across the same side of the bond. Remember when we talked about the trans or anti-addition we saw in adding a bromine across a double bond? One of the bromines ended up on top, the other ended up on the other atom on the bottom. That's anti-addition. In this case, both the hydrogen and the boron end up on the same side of that double bond. That's syn stereo addition, okay? So the regioselectivity says that our hydrogen adds to the more substituted carbon, the reverse of Markovnikov's, and the boron adds to the least substituted carbon, okay? And it means that it also adds the hydrogen on the boron on the same surface. This is most easy to see when we look at alkenes and rings, because we can show you that the H and the boron both added across the same side. So in the case of this right here, this methyl cyclopentene, now this is a secondary carbon and this is a tertiary carbon. And because it's anti-Markovnikov, that means we're going to put the hydrogen on the more substituted carbon and the boron on the less substituted carbon. But because it's syn addition, they're going to add across the same side. So when we do this, that means the hydrogen is going to end up on the same side as the boron right here, giving us our product. And that's if it attacked from the bottom. If it attacked from the top, it's actually going to give us this other product here where the hydrogen and the boron are still on the same side, but that's coming at the top of the double bond. Okay, so we're going to get equal portions of both on the top or both on the bottom. Okay, so the reason we account for this regiospecificity and the syn addition is the fact that the alkene doesn't reach out and grab the hydrogen selectively as a positive charge and pull it into it to create that sigma bond. What we think is happening is the boron's actually slightly more electropositive, and therefore the hydrogen is slightly more electronegative. So it no longer acts as that Lewis acid. It's actually acting as the Lewis base. And so what we end up getting is that because the hydrogen side is partially negative and the boron side is partially positive, we get the addition of we start to form a carbocation. When we start to form that carbocation, it's going to be on the more substituted side, meaning the more substituted end. So if we have that partial carbocation on this atom here, and the hydrogen is the more electronegative of the two atoms, it's going to bond to that. And because it's happening all at once in this kind of four-membered ring happening here, they have to add on the same side. Okay. If they tried to add in the opposite direction, we would have our partially positive, our forming carbocation be on the primary carbon or the less substituted carbon, and it would not add as well. So being that we have this partially negative hydrogen and a partially positive boron, it's going to add across, giving us our more stable, partially positive carbocation. Okay, so that's how we do the hydroboration reactions here. And in the alcohol chapter, we'll learn how to oxidize off that boron to create that alcohol. But now that we've actually added hydrogen double bonds, we're going to show you additional reactions on hydrogenation of alkenes. Okay, so what we can do is we can actually take hydrogen and just add that across an alkene as well. But the hydrogen-hydrogen bond is not very polar, and the alkene itself is not very polar, so we actually typically use a catalyst to activate that hydrogen bond such that we can add it across the double bond. And what we call this is catalytic reduction or catalytic hydrogenation. And most of the time we use things like palladium, platinum, and nickel, where we have the hydrogen adsorbed to the surface of the metal. And notice occasionally we use a little bit of pressure associated with here to get that hydrogen to adsorb to the surface of the metal, and then we get addition of the hydrogen onto the alkene. Sorry. Okay, so if we're making this and we have to have this catalytic hydrogenation where we have to have the hydrogen adsorbed to the metal first, that tells us something about the regioselectivity. Okay, so again, let's think about, because these hydrogenations are syn addition, okay, why are they syn addition? Okay, so our first step is those hydrogens attached to this metal surface, okay? And now our double bond has to float down to where this surface is. And since both that whole side of that double bond is coming down to those hydrogens, that means that both of those hydrogens are going to add on that same side because they're all attached to the metal at the same thing. So we can look at the hydrogen and the alkyl are both absorbed on the surface of that. We're going to transfer one hydrogen first, and then the next hydrogen second, because it's still attached to the surface. And once we attach that second one, it can now not be bonded to that surface anymore and drift away and is released as our saturated hydrocarbon. Okay, we had an alkene, which is an unsaturated hydrocarbon. We've added hydrogen to it. It is now a saturated hydrocarbon. And it's syn addition because everything happened at that surface. Everything has to happen on that same side, or syn addition. Okay, so let's talk about a way in which we can measure the stability of an alkene or alkane. And we do this by measuring the heat released during hydrogenation. Okay, so if you release just a little bit of heat in hydrogenation, that means you didn't store very much energy. But if you're releasing a lot of heat, that means you had stored a lot of energy in the system. Okay, so we can get a relative stability of our double bonds by looking at the heat of hydration and how much heat is liberated. All right, so if we look at just the ethylene right here, which is just the two carbons right here, and we add hydrogen across it, we release 137 kilojoules per mole, okay? So if we're releasing 137 kilojoules per mole, that gives us, okay, that's where we're starting from, okay? Now, if we take propene, which has one more carbon on it, and so that one of those carbons on the alkene is substituted, we actually release just a little less energy, okay? You know, about 9 or 10 kilojoules per mole less, okay? And by adding more and more longer carbons here, we don't see a change, okay? So this change in energy drop has everything to do with the fact that we have one extra carbon, we have a substituted carbon on our double bond, okay? So that's the difference in this energy here, is the fact that there's really no difference in energy between having just that one substituted carbon on that double bond or having no substitutions on that double bond. All right, now, if we go to a different isomer, we put a methyl group on each side, so we have one methyl group on each of those double bonds of the carbon, we actually release a little less energy, meaning that having two carbons, one on each of the alkene double bonds sides, actually releases less energy, which means that having two carbons, having a carbon on each of the double bonds is more stable than having a carbon on just one side of the double bond. Now, if we look at this trans isomer here, it actually releases even less energy. That means that this cis isomer here, because these methyl groups are pushing out at each other, there's more energy stored in that than in the trans. These two are opposite each other. There's no tension between those. Therefore, it's even more stable. So the carbons bonded to the double bond are giving it the stability. Okay, so if one carbon gives some stability, and then two carbons on these two give more stability, what does three carbons bonded to that double bond do? It actually makes it even slightly more stable, releases a little less energy, and when we get to 4 different substitutions of carbon on there, we get to our least amount of energy released possible. Okay, so what does this tell us? Is that an alkene with no carbon substituents is the least stable. By adding one carbon, we gain some stability, but then as that chain grows, there's no additional stability added. We have to add another carbon to that double bond. So once we have 2 carbons to that double bond, it's more stable. But the cis is less stable because of they're butting up against each other. The trans is more stable because they're further away. And then a third carbon to that double bond is a little more stable, and that fourth carbon is even more stable. Okay. Okay, so this is the result of what we just talked about here. Reduction involves a net conversion of a weaker pi bond to a stronger sigma bond. When it does this, the greater the degree of substitution on the double bond, the lower the heat of hydrogenation, okay? The greater the degree of substitution, the more stable the double bond was. The trans alkene is lower in energy than the cis alkene, meaning the trans alkene is more stable than the cis isomer, okay? And the difference is due to the non-bonding interaction between those R groups, or those carbons, in the cis alkene. Okay. Ooh. All right. So let's do our last slide on heats of hydration. Okay. So this is another example of just comparing cis and trans to butene. Okay. So the difference in energy between the cis compound right here and the trans compound right here has everything to do with these methyls groups coming up and interacting with each other. Because they're coming up and interacting with each other, they're straining the bond, they're pushing it out like this. And we can measure that change in energy as 2 kilojoules per mole, 4.2 kilojoules per mole, because that's the difference between having it there and not having it there. Once you get the trans, you have no more strain. These are just floating out in space. In that cis, it actually releases more energy. So it's the less stable of the double bonds. Okay, now stay tuned for the last version, part number 7. We're going to talk about reactions of alkynes.